Today we start the first lesson of uh, digital communication. In colleges, of course, we used to, in short, call it DCOM. Anyway, this is the first lesson of digital communication. So it's an introductory lesson in which we shall see why we are really going for digital communication. First thing you see, all natural signals are analog. But we are going for digital communication. What I mean by all natural signals are analog, right? When we speak, let's say, we create sound and we speak, the signal that the mic creates is an analog signal. When any one of us speak, we do not speak in the form of pulses, like kick, 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 kick. We do not speak like that. We make words, we make modulation of the sound. It's an analog signal. Even when any sound in the nature, it's actually an analog signal. Like this, it's actually an analog signal. There's a time axis and it's a signal strength or signal amplitude axis. It's a continuously time varying. It's a single valued function and it's a continuous function which varies with time. For example, if you have a mic, you are speaking to a mic, the output voltage of the mic or output current of the mic is something of this shape. It is not in the shape of pulses. It's not digital signal. So first thing we observe that all natural signals are actually analog signals, but almost all communications are digital. Why? Actually, the revolution of communication engineering started sometime during the First World War. Then after Second World War, it was further revolutionized. And then everything became digital. Why we go for digital? In digital communication, there is a transmitter and there is a receiver. In analog communication, let's go back to analog communication. In analog communication, the current or voltage produced by the mic is amplified and then transmitted through two pieces of wire as a two-wire cable to the other end, like the telephone lines of the old days, of the telephone lines which existed something around 30 to 40 years back. It was analog signal transmission. But today in a digital system, there is a transmitter on one end and there is a receiver on the other end, and a series of pulses flows through. The pulses are of actually voltage pulses, and pulse height can be 5 volt, 10 volt, 3 volt, anything as per the design. And normally, for the sake of convenience, when there is a pulse, we call it 1, binary 1. When there is no pulse, we call it binary 0. So we also call it 1001, something like that. But actually, they are voltage pulses. Now, why do we go for digital signal? It is because in digital communication, the original digital signal can be reconstructed or regenerated from the received signal distorted by the noise. Noise is the main enemy of any communication. Like, suppose you are in a crowd, you are shouting to somebody at the other end of the crowd. He will not listen to hear you properly because of the environmental noise. Same thing happened in electrical communication signals also. There are so much of noise around, electrical noises produced by mobile towers, noises produced by car engines, magnetic noise, and the enormous source of noises. They distort the signal. They distort the analog signal and they distort the digital signal also. But if it is a digital signal, the original signal sent by the transmitter can be reconstructed. There is a technology available. But the same is not possible for analog signal. In, I should say, practically not possible. Theoretically, by using mathematics, you may make it possible, but practically it's not possible. And that is why whole the entire communication system has already come to digital system. Next, we go to a digital communication channel. Now, in this channel picture, I'll show you a complete channel, which you will find it difficult to understand today, but just keep the diagram in mind, because each part of the channel is a separate subject in your engineering course. Firstly, there is somebody who is speaking, right? Somebody who is speaking. The signal can be anything, speech signal. The signal can be from a temperature sensor, signal can be from any kind of sensors. But let us take the example of speech. That is easy and most common example. Somebody is speaking, he is creating a sound wave, and then there will be a mic. What this mic will do? What do we call the mic? This mic is actually, what we have learned, is a transducer which converts the sound energy into electrical energy. So output of the mic is an electrical signal. The signal which I showed you just a few minutes back, it's a continuous time varying analog signal. Now, in a communication channel, this is how the analog signal looks like, right? Then there will be a system or subsystem which is called source encoder. Now, what is source encoder? We shall learn step by step. What this source encoder does, source encoder converts this analog signal into a series of pulses, right? Then comes a line coder. Now, this source encoder, we give this signal from source encoder to a long distance channel, the pulse train will not survive the distance. It will get attenuated and there will be a lot of error, etc. So there is a subsystem which is called line coder. Line coder converts it into a same pulses but of different shape. Like I tell you, out of source coder, this is 101. Here, 1 is a positive pulse, but 0 is a negative pulse, right? So this conversion is done for, it has got certain purposes which we shall see gradually. Then after line coder comes the channel coder. Channel coder converts it into another series of pulses. Like say, the source coder pulse was 1, 2, 3, 4, 5, 6, 6 digit or 6 bit. Line coder also 6 bit, 1, 2, 3, 4, 5, 6. But channel coder output is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it increases the length of the signal, length of the pulse trend. There are certain need of doing it, right? It is need for making any error correction. If at the receiving end, receiver identifies some error has occurred, it will correct it if it is already channel coded. After channel coding comes the modulator. Now, these digital pulses of 5 volt plus minus, if you cannot put it through a piece of wire and send it to 1,000 miles away, it's not possible, because it will not travel even 100 meter or 1 kilometer. So there is a modulator. What the modulator does, modulator has a built-in oscillator of certain frequency, what we call carrier frequency. And this carrier frequency is modulated by the pulses of the channel coder. Like say, in the channel coder output, it was 1101. Here you see the first two ones, the carrier frequency is full length, full amplitude, and for zero, carrier frequency does not exist. Again, for next one, carrier frequency exists. Like this, when there is a carrier frequency, like the frequency you hear that the telephone line, your mobile works at such and such frequency, your TV works at such and such frequency, some megahertz, gigahertz. This is the carrier frequency. After modulator is the energy conversion. Sometimes they ask you viva questions in the channel, where is the energy conversion? One, you have seen the energy conversion at the mic. Another will be energy conversion here. Before transmitting energy conversion, this modulated carrier will be converted into either to pass it through or to be transmitted by a radar, or to be transmitted by optical fiber, or maybe it will create data packets to be transferred through internet protocol. So there will be a energy conversion. After energy conversion, suppose this microwave communication, microwave uh, microwave transmitter, it is communicated, and maybe it is communicated 100 kilometers to another receiver radar 100 kilometers away. In this path of 100 kilometer is the major noise effect. Of course, be very clear that noise affects every part of the transmission system. Noise affects source encoder, line and channel coder, everything, because all of these are electronic equipments. All the electronic equipments have got electrical components, and every electrical component will create some thermal noise. But such noise can be minimized or controlled by more and more advanced design. But when you transmit the signal through your transmitter and it is received by the receiver, you cannot do anything because the microwave communication is going through thin air. This is the part where the environmental electrical noise affects the communication system. Actually, this is the devil of the noise who is sitting here. Then it is received at the receiving end. Receiving end does the reverse energy conversion. It creates the same carrier modulated waveform. Then there is a matched filter and demodulator, which creates the same waveform which was out of the channel coder at the transmitter end. Then there is a channel decoder, which creates the same waveform here. And then there is a line decoder. Actually, on the transmitting side, you have got the electronic functions, which are reverse of the functions of the receiving side. Then, after the line coder output, then it goes to a source decoder and then to a speaker. Speaker creates the same sound. This is a complete digital communication channel. Now, mind it, each of these boxes are a separate subject on the communication theories, and you have to learn them separately. Next, just for your note, that after you learn the digital communication theories, the other things that will come for your communication engineering is discrete signal processing, which is called DSP, Then comes error control coding. Just in last one, we have seen the channel coder. Channel coder performs the error control coding. Then mobile communication, optical communication, satellite communication, computer communication. These are the various subjects, different subjects that we have to learn. Uh, we have made one statement. Original digital signal can be reconstructed or regenerated from the received noisy signal, which is not possible in case of analog signal. I want to show you a schematic, uh, why I am saying this, why it is not possible for analog signal and possible for digital signal. Now, for that, I'll switch over to another screen. So, your computer screen will go blank for 2 or 3 seconds. Just hold on. I'll switch over to another screen. Now, this is the new screen. This is a model of a analog repeater. This is the where signal is generated, and this is the noise source. This is a schematic diagram, and noise source is added to the signal in a adder here, right? And there is an oscilloscope. The first channel of the oscilloscope you see is connected to the signal. So first channel of the oscilloscope will show you the signal. Channel B of the oscilloscope will show you the noise. Channel C of the oscilloscope will show you the adder output, that means noisy signal. And channel D will show you that, see, output of this noisy signal. Here, I have added a low pass filter. Because suppose your signal has a bandwidth. Suppose your signal has a bandwidth of 10 kilohertz, audio signal, let's say. So you can use a low pass filter of band 10 kilohertz, so that higher frequencies which are noise frequencies are eliminated. But I will show you complete elimination is not possible, because noise, when you learn the noise chapter, you will find noise contains all frequencies from almost zero to infinity. So there are noise frequencies even within 10 kilohertz. By best filtering also, you cannot remove that noise. And when you hear to that noisy signal, you see the voice is distorted, or the song you listening is distorted. I'll show you how it works, right? So let us uh, look at the oscilloscope, and let's run the signal, run the system. The system is running. The first channel of the oscilloscope is the signal. You see, it is a clear signal. Second channel of the oscilloscope is the noise. Third channel of the oscilloscope, you remember, third channel of the oscilloscope was connected to a noisy signal. That means this is when this signal, original signal and noise is added. This is noisy signal. Now, fourth channel of the oscilloscope is connected to the filter output. So the filter, just observe the filter output properly. The filter, this is the first one is my original signal, and the fourth one is the filter output. You see, output is still noisy. You just cannot remove this noise. It's not possible, because noise has all frequency components. If you have a baseband signal of 10 kilohertz band, then even within 10 kilohertz, the noise exists. And how can you remove that? If you remove that, then your signal itself is lost. I shall also show you the spectrum. This is the spectrum of the original signal. This is the spectrum of the noisy signal. And this is the spectrum of the retrieved signal after noising, after filtering. I shall run the system once again. See, this is the frequency spectrum of the original signal, right? This is the spectrum of the noisy signal. So the signal, even in frequency domain, it is so much distorted. And this is the spectrum of the filtered signal. You see, there is hardly any difference between the spectrum of noisy signal and spectrum of filtered signal. So it is just not possible to remove the noise, right? Now let us see a digital function. This is the picture of a digital repeater. Here is a digital signal generator and here is a noise. These two are added. So noisy signal is given to channel C of the oscilloscope, the original signal in channel A, the noise in channel B, and what is done here. Okay, let me uh, start it and then you shall see, right? Okay, this is the original pulse train digital signal. This is the noise. Now you see the pulse is affected by the noise, right? So what we can do here, once pulse is affected by a noise, simply create the channel 4 of this oscilloscope, four channel oscilloscope is the output of a differentiator. Or you can say low pass filter also, or high pass filter, or low pass filter also, output of a differentiator. Now, output of the differentiator, this is the noisy signal, and output of the differentiator is like this, which also creates pulses, but this is noisy pulse, but less noisy. Some noise is removed. Then what do you do? Then what do you do? This noisy pulses, there you can give it to a comparator or any kind of flip-flop, a very simple circuit. With the help of this noisy pulses, you create straight pulses. With the edge of this, you create straight pulses. If you do that, you will see here, I have added another oscilloscope here, which number one input is the signal and number B input is the pulse shaper, which is this pulse is shaped. This is a noisy or deformed pulse which is shaped and given to this oscilloscope. You see, oscilloscope was already running. Here, this is my original signal, and this signal, distorted pulses, were given to a pulse shaper, and we are back to the original pulses. The idea is they have distorted pulses, but with simple digital circuits or even with the help of analog circuits, very simple circuits, with the help of distorted pulses, you can always create perfect pulses. So we are back to normal pulses. So this was the first step or introduction. Next day, we shall go to the chapter of sampling. This we want to convert the analog signal into a series of pulses. How do we do it? For the sake of speaking, it appears to be not very difficult, but there are some difficulties. We shall go to the sampling theorem next day. Okay?